Ladies and gentlemen, please welcome Corporate Vice President Brad Anderson.
It is just awesome to see this many people here at 5 o'clock for this second keynote. Thank you so much for coming. I think you're in for a real treat. So we thought we'd end today by looking at the future. And what we thought we would do is give you a glimpse into some of the things that we're doing as we think about the next generation of technologists that are coming up, but also share with you some of the things that we do in Microsoft Research, which is one of the most amazing organizations in all of Microsoft. Now, we talked to you about what our vision is and what our mission is. And our mission is to empower all people and all organizations around the world to be able to achieve more and to be able to do more. And as we think about how we implement that, one of the things we spend a lot of time on is we spend time on how we work with youth. And so specifically, we announced a program back in 2002 called YouthSpark. I'm curious, how many of you have heard of YouthSpark? Okay, well, we set out with a goal in 2002 to be able to touch and influence 300 million youth around the world by 2015 and help inspire more youth to look at computer science, to look at the mathematics and the areas in technology as we think about this next generation coming up. Here we are, 2.5 years into this. We've already been able to touch 227 million teenagers across 100+ countries. You know, it's a wonderful partnership with over 30 programs and with 130 different organizations around the world that we deliver this. Now, one of the elements of YouthSpark is a program that we call Imagine Cup. Imagine Cup is one of these wonderful competitions where youth from around the world can show off their innovation, can show off the things that they're doing from a creative standpoint. And it gives an opportunity for them to show off their ingenuity in areas like games, in integrated solutions, and applications. I mean, the gambit is wide open with where they focus on what they work on. Let's actually give you a view of what Imagine Cup looks like and come back and talk with actually the 2014 winners. So let's take a look.
We are the future. We live in a time where we can imagine the impossible and make it probable. There is just boundless imagination and the possibilities of what technology can do to any walk of life. Innovation is something that's truly inspirational.
My name is Gerald, and this is Jennifer. We are Team Anemia from Monash University.
It is the world's first simple, non-invasive, and easily accessible tool for screening anemia.
Very impressive, and we'll get some people talking to you about the next step.
Imagine Cup.
Imagine Cup.
Imagine Cup.
Okay, Imagine Cup. What a wonderful and incredible opportunity for youth around the world to be able to show off their ingenuity. I can't even imagine what it'd be like as a teenager to be able to come in and represent your company in a global competition like that, and then the winners to actually sit down with Bill and with Satya and have a conversation about what they're doing. And so with that, do me a favor. Let's give a warm welcome to Gerald Saya and Jennifer Tang, the winning team from the 2004 Imagine Cup. Give them a warm welcome, please. All right, so Gerald and Jennifer, coming to us from Australia via Skype. Tell us a little about the name of your project and exactly what it is.
So our project's name is iAnemia, and it is a way to screen for anemia, which is simple as taking a selfie. But I think the best way to tell you about this solution is about where it started. So the two of us thought about this idea when we were in our 4th year of medicine. And we were doing our women's and children's rotation in a town 6.5 hours northwest of Melbourne. Now, during the second week of my rotation there, I went to a town an hour out from this small town. And there I met a woman. She was 35 weeks pregnant and came in with 3 children under the age of 5. She was explaining to me how tiring it was needing to travel into this clinic for blood tests, and this clinic was the closest to where she lived. But perhaps the thing that shocked me most was when she told me that she had friends who lived in rural farms who just didn't come in because it was too difficult to access these clinics. And this is where Jarrell and I sat down and we brainstormed ideas to better enable screening within the home. And this is where we thought of iAnemia, a simple and objective method for screening for anemia.
So with the iAnemia, tell us what the development process was like.
So with iAnemia, we first started working on this idea back in May 2013. And when we first looked at the problem, we thought, what do humans do? What do doctors do? How do doctors look at a patient and say, this patient might be anemic? And it turns out that they look at the color of the lower eyelid, so just the inner lining of your lower eyelid. The more pale that is, the more likely someone is to be anemic. But that's a very subjective process, and so we decided to try and package all of that medical experience and put it in the hands of users so that they could take a photo of their own eye and predict their own risk of anemia. And along the way, we've had lots of challenges, lots of technical as well as business challenges, but we've been working on them, we've been iterating through our product, and we are confident that we can make a change in the world.
So tell us what you've been up to since you actually won the Imagine Cup.
Well, the Imagine Cup in itself was an amazing opportunity, and it has really helped us to challenge us on a daily basis to think about how we can find solutions to problems we see on a daily basis. When we entered the Imagine Cup early last year, we did not think there was any opportunity for us to win it. So we were very, very surprised when we ended up doing so. Since winning the Imagine Cup, we've had the opportunity to meet many inspirational people, such as Bill Gates, and we've been able to share ideas in different platforms overseas and within Australia as well. And it's been an amazing opportunity for us.
All right, so what's next? What are you working on now?
So right now, we're working, bring iAnemia into the hands of users. But to do that, what we need is a lot of data. So what we're doing is undertaking large research trials. We're getting thousands of photos, we're getting thousands of blood tests. We're validating our solution, and we're going to build it upon the foundation of rigorous research and evidence.
Well, there you have it. You know, you've got several thousand people in the room here. I don't know if you can see all of us, but you've literally got about 10,000 people here, right? And you know what? Let's give them a big round of applause and congratulations. Phenomenal work. Awesome. All right, thank you. You know, to me, that's just amazing. You know, I think about what that next generation is going to look like and how they're going to change and influence the world. And there are very few things that inspire me more than that. You know, and at Microsoft, since our inception in 1975, we've always been optimistic about the future and how technology would play a role in the future. You know, and today we talk about the transformation that is happening, and at the core of the transformation in every company is software. You know, if you really look at what's happening, every company in the world is becoming more dependent on software, more dependent upon technology. And so with that in mind, I think the optimism that all of us should have in terms of how technology can improve all of our lives, make our personal lives and our work lives better, is just unbounded. And so with that, let's actually now take a view of what's happening as we go forward. And so what I want to do here is introduce to you, honestly, who I think is one of the most incredible, most genuine people that we have at Microsoft, Harry Shum. Harry's an executive vice president. He's been at the company for a long, long time, and he leads some of the brightest minds in the industry in terms of computer scientists. He leads the organization that we call Microsoft Research, and Microsoft Research has a global footprint where you've got these really special individuals who have that determination to really prove something that's never been done before in the past, coupled with that technology vision and that technology capability to actually make it happen. So I think you're in for a great treat. We're going to give you a peek at what we think the future could look like. We're going to give you a peek in how we think technology can change our lives as we go forward. So with that, please welcome Executive Vice President Harry Shum.
Thank you. Welcome. Thank you so much. Yeah. Hello, Ignite. Good evening, everyone. I'm so excited to be here, and especially watching those kids, the winning Imagine Cup at the backstage. And looking at those kids' genuine smiles reminds me that we were all once young. And we are so living in such a great time, and the technology is changing everything. I'm so happy for those kids. I have very much enjoyed the conference, as I know this is the first time we have Microsoft Ignite. And this morning, started with Satya's keynote, and we listened to 3 great presentations by Joe, by Gadeep, and by Brett, talking about those exciting progress we have in Microsoft. I also had this opportunity to tour the floor a little bit for a little over an hour, talk to some people from big companies and some people from small companies. Interesting thing I noticed is how much those people, those companies, our partners like you, actually understand and leverage Office 365, especially Office Graph. The demos are very, very interesting. I do understand that it's already past 5. I'm standing between you and the reception. I understand the cold beer waiting for you guys. So I really hope this session is going to be interesting and helpful to you. And I'm going to show you, with the help of my colleagues, a set of interesting projects and the demos, and get you excited about what we have been thinking about the future of computing. Let's get started. Thank you. I hope I can get more applause later on during my presentation. I'd like to start with this quote that many of us in tech industry actually really like. I was pleasantly surprised to see this morning in a video that the professor from Virginia Tech quoted exactly the same from Arthur C. Clarke. I think many of us in tech industry really, really enjoy this quote, because not only we actually had this opportunity to create a lot of magic products and the magic technologies, but also we benefit tremendously being in IT, having the opportunity to create unbelievable products that get deployed to the users. Of course, many of you doing that every day in your daily job as well. That's actually what's getting us really excited about. But as I think about the future, I look at what we already have today. If you think about all the big data, machine learning, artificial intelligence, powerful algorithms, mobile, clouds, all those things, I strongly believe that the future breakthroughs are going to be not only more exciting, but also more invisible. So I'd like to start with Satya's 3 big ambitions for the company. This morning, Satya outlined 3 big long-term ambitions for us. The first one is creating the more personal computing. The second one is reinventing productivity and the business processes. The third one is building the most intelligent cloud. Those are really, really long-term ambitions. But But at its core, they are really about having people experience technologies in their daily lives, at work, at home, and anywhere in between. These ambitions are about hardware, about software, about enterprise, about consumers. But the most important is about the ecosystem that we all together with IT pros, with our partners, we are generating together. To accelerate the progress, we have been investing across all these areas, and we must, along the way, solve many challenging technical problems. That's actually what I want to talk to you about today. As the head of technology and the research group at Microsoft, so my job is really about pushing the technology boundaries. And together with my team of world-class computer scientists and advanced development teams to support the company's bold vision and ambition. Put it simply, our job is actually about searching for the next big things. Not only about the next big things in terms of technology innovation, but also about the right product categories and disruptive business models as well. But there is a big difference what we do in our division. We focus on solving a whole set of problems that most people don't even know about yet. So that's why we actually think about what's really happening now. What have already happened? If we look at yesterday's achievements, look back last 5 to 10 years, I would say probably most of us got very, very excited about those things that are visible, that are physical, that we can get a hold and we can touch. Those are gadgets, those are phones, those are tablets, those are gaming consoles. Those are emerging Internet of Things. Those are wonderful. But keep in mind, those magical products, those things, they are magical, partly, significantly partly because what's actually inside the device, the software, the powerful algorithms, those things made the devices interesting. And as I look forward, thinking about tomorrow's breakthroughs will be a lot more invisible for two very, very good reasons that actually Satya outlined as mobile first and the cloud first. As computing shifts to the cloud, there's just a tremendous opportunity there that with huge amount of computing power, unbelievable amount of storage, probably most interestingly, the kind of collective intelligence that we can harness from this huge amount of data, the intelligence we can extract from that, that is where we will see a lot more magic happening. At the same time, we are talking about mobile first in the sense that the user keeps moving. The user keeps moving to different environments where the user can actually interact with the computing ecosystem, other devices, such that more magics can happen there. It is this set of tomorrow's breakthroughs that we are focused on that actually can take us to the new heights, the new breakthroughs. But that requires us to have a strong mind of playing long games. Indeed, in research, we play long games. We play long games. We think about those kind of problems in the future, probably 10, 20 years earlier. Many today's breakthroughs benefited from investments 10, 20, even 50 years ago. I very much like a quote something actually Bill Gates told us in the company. Bill said, people tend to overestimate what they can get done in a year. But the people vastly underestimate what they can achieve in 10 years. It's very, very important for all of us in IT to have this strong mindset of playing the long game. We are here to stay. We are here to innovate for a long, long time. Microsoft is here to innovate together with partners like you. I give you a couple of examples to make this concrete point that how we have benefited from long-term investment. The first example is Kinect. The Kinect sensor for Xbox. When Kinect came out several years ago, it was really breakthrough. It's very innovative. It's the first time people realized that, oh my God, you can play games not with the controllers. You can actually play the video games with yourself. You are the controller. How could you even do that? Well, that's because the technology enabled us to track the human skeleton so that you see the human movements, and then you can play games. That's why the dancing game became extremely popular, because everyone can dance a little bit. So the technology, in terms of skeleton tracking, using two-dimensional and the three-dimensional images, happened several years earlier. Then through the genius of our product people, we were able to put together this incredible experience for gamers. I tell you the second example. Actually, Joe showed this morning in his keynote with the latest Microsoft browser called Microsoft Edge. When you are in reading mode, even if you look at some web page that is written in foreign language that you may or may not understand very well, we are able to convert that page into your native language. Let's just say American English. So you can actually read that. But we started investing in natural language processing, natural language understanding, machine translation long, long time ago. In fact, the first research group we ever started at Microsoft 24 years ago was natural language group. So we're very, very pleased to see that incorporated into the latest browser. You may also have heard something called the Skype Translator that we recently rolled out that can allow the users from both sides speak different languages. We roll out a few languages right now. We have more languages coming. So that really shows the commitment from Microsoft to be in the long game. But you might ask me, so how did you organize your team of 1,100 world-class computer scientists worldwide? What do they do? Are they just every day just dreaming? Or look at the blue skies? Well, yeah, that's how we started. We do have basic research. We have basic research. People think about all kind of curiosity-driven research projects. We cover the entire spectrum of computer science. Almost any kind of computer science problems that's interesting, we think about it. Then we look at all those interesting results we get. Then we look at what kind of products we do in Microsoft. Then we rapidly transfer those technologies into the product teams. I mentioned to you about Kinect. I mentioned to you about the browser. But there are many, many those products. I would say practically every major product line in Microsoft has benefited from the research result from Microsoft Research. But we don't stop there. Then we also look at some really interesting areas and the projects that we see the potential to create new product features or even new products. Then we run in more or less like a startup mode, have a small team of the projects, then we actually go with that. Then we have this mode of operation we call the fast forward or fast forward. Again, very much like how VCs fund the startups. And then we have all those interesting few Microsoft scale investments that we believe that we can have this opportunity to create Microsoft category products with millions of users that we found. And we think about if there is actually economics model there, business model there, pricing model there, that actually makes sense for Microsoft. But then again, what I really want to talk about today are those interesting technical problems. Especially, I picked 3 big problems to solve. These 3 problems are data, compute, and intelligence. Let me start with the first one. The first problem is something that I believe everyone in the room is acutely aware. That is, my God, we are going to have a lot of data. What are we going to do? If you haven't really noticed, let me tell you, by some estimate, in year 2019 or 2020, there will be 25 billion intelligent devices everywhere. 25 billion. And they will generate more than 44 zettabytes of data. As you think about, at the home or at your workplace, we will see those number of intelligent devices outnumber human beings by a factor of 5 to 1, 10 to 1, or even 100 to 1. Without you paying attention, they generate a lot of data. And this amount of data, if you don't pay attention, is not only going to be useless, it will become a distraction for you. It's going to be a headache, especially if you work at the IT department. You really have to really think about what to do. So that's why the Microsoft will have developed products recently, products like Power BI, Office 365 dashboards, to help you to look into the data, look for the insight. But we have more technologies in Microsoft Research that we can actually deal with the data and with very, very interesting user experience. So I'm going to invite my colleague, Curtis Swan, to come to the stage to show you what kind of innovative data visualization technologies we have been developing in our labs. Curtis.
"15 years ago, Turing Award winner Jim Gray saw the future challenges of big data and began working with astronomers who were collecting terabytes of data every night as part of the process of mapping the large-scale structure of the universe. Jim got me involved because he realized visualization and analytics were needed to help find answers when we didn't always know the questions. We built Worldwide Telescope to bring together hundreds of terabytes of data and imagery into one coherent visualization of the universe that I launched in TED in 2008. Let's have a look at that, those of you who haven't seen it. So what you're looking at here is a visualization of the large-scale structure of the universe. Each dot is a galaxy. Each galaxy is 100,000 light years across and has hundreds of billions of stars in it. And there are millions of galaxies in that visualization. Our early investment in the technology to build Worldwide Telescope provided us with a deep understanding of how to build complex spatial temporal data visualization at home. The 20 million users of Worldwide Telescope included kids of all ages. So we learned a lot about designing software that would be easy to use and would scale globally. Soon after the launch of Worldwide Telescope, we created a team, a startup team, to leverage that technology and build PowerMap so that anybody could easily visualize data from spreadsheets all the way to really large data cubes. Let's take a look at some data about Chicago, which is the narcotics activity over the past few years. Now, in creating this visualization, it only took me a few minutes, but in just a few seconds, you can quickly see the footprint of the problem and the growth of it over time. So now you've seen the 15-year roadmap from Jim Gray visualizing the large-scale structure of the universe to Worldwide Telescope to PowerMap, when we're really excited to be able to show you our latest work in visualization, which is NuiGraph. And I'd like to introduce Dave Brown to come up and show it to you. Dave?
Thanks, Curtis. I'm fascinated by the potential of computer graphics to solve problems in the real world. One of those problems is trying to make sense of data, which continues to grow both in terms of size and complexity. The demo I'm going to show you today, called NuiGraph, leverages both computer graphics and our incredible ability as people, as humans, to process vast amounts of visual information, to find patterns in that information, which ultimately lead to insight. So let's jump in. This app's been written on the Universal Windows platform, so it runs beautifully on the Surface Hub. So let's make it full screen. And I'm first of all going to load some data. I'll go to my data control and load a file which contains a spreadsheet with about 42,000 rows of data. So a relatively small data set. It's a data set I downloaded from the web, and each one of those rows of data represents a tornado that has taken place in the United States over about the last 40 or so years of US history. Now, coming from the United Kingdom, I didn't know very much about tornadoes, and what I want to do is share with you a journey through this data set where I explored it using this tool, and I want to share with you the insights that I found along the way. So right now, you can't see any data on the screen because I haven't told the app how to map this data spatially. So I'll start by going to my spatial control, picking the axis along this side of the screen, and going to one of the columns in my spreadsheet, longitude, placing it on that axis. Then I'll pick another axis and go to another column in my spreadsheet, latitude, and place it on the screen in that direction. So instantly you're seeing an outline of a map. And there's no map on the screen, but there's a sufficient number of points to make out a map of the United States. Now, this doesn't tell me very much, except that tornadoes tend to take place pretty much everywhere in the United States. And what I should say is that each one of these rows in the spreadsheet, all 42,000 rows, are being drawn as a cube on the screen here. So we've got 42,000 cubes on the screen. Clearly, a lot of those are being drawn over the top of each other, so I need to try and clean that up a little bit. And I'll start by applying a size to each one of those cubes. So I'll go to my size control, and I'll apply another field in my data set, the strength of the tornado, which goes from 0 being the weakest to 5 being the strongest. And I'll apply that to each axis of my cube, each side of my cube. So now I've got 42,000 uniform cubes that have been scaled according to the strength of the tornado. And I'm starting to see some patterns emerge in this data. I have a cluster somewhere around Colorado. I can see some clusters around the mountains in California. I can see some clustering around the coastlines in Florida, for example. So some structure is starting to reveal itself. Next, let's apply a color to that. I'll also pick the strength column to apply, where blue is the weakest of the tornadoes, and the larger white squares are now the strongest tornadoes. So you can instantly see that there are typically the larger, very destructive tornadoes take place in the mid to the eastern portion of the US. So that was the first learning. Now, what this doesn't tell me is how frequently tornadoes take place. There's still a lot of overdrawing going on here. So what I'll do next, rather than use these controls to manually step through these mappings, I'll pick a preset that I found when I was exploring the data earlier. And this one grids the data and stacks it up according to how many tornadoes occurred in that particular grid square. So all I did there was stacked it, gridded it and stacked it. So you can see from the heights of these bars how many tornadoes have taken place in a given grid square. And you can start zooming in and flying around this data. I can see, for example, Texas has got a lot of tornadoes. We can see those peaks around in the Colorado mountains and those ones in Florida. But again, and you can also see that Chicago is not immune from tornadoes, which we should be aware of. It's pretty safe over in Washington, where I live, but certainly they're not immune in this part of the United States. So now I've got an idea of how frequently tornadoes occur, but not when they occur. So let's switch to another view. Let's just jump back for a second to a two-dimensional view. This is just mapping latitude and longitude and sizing by strength. There's another column in my Excel spreadsheet, which is time, the time the tornado occurred. So what I want to do is pick the third dimension of this graph and apply time to that axis. So what I'm doing here is I'm effectively stretching out a map of the United States. I'll just undo that for a second so you can see that again. And pulling that data out, so you're effectively looking down a core sample through the United States over the last 40 years or so of tornado history. And there's a couple of things that jump out to me. Actually, I'll put color back on first. So it's color by strength again. There's a couple of things that jump out to me. The first is that I can spot a cluster down here in the bottom part of the graph. So I'll use my filter control, zoom back to about 1975, it looks like, add that as a filter just to discard the rest of the data temporarily and zoom in on this guy. So there's a definite cluster of data around here. And I'll just use the pen to select one of these guys for reference. And actually, I looked this up on Wikipedia after I found this cluster, and it was actually given a name, the super outbreak of 1974, back in April 1974. A very destructive set of tornadoes, and very, very easy to find that cluster using this tool. So let me zoom out again. I'll remove that filter to go back to the whole data set and reselect the entire set. And we can see our selected tornadoes still visible. So I now know something about a couple of interesting clusters. But the other thing that was interesting about this data set is when I look at this, I can see some banding taking place, some layering in the data, which suggests some periodicity, some seasonality to tornadoes, which makes sense. So how do I investigate that further? So I can use the time column not as chronological time from 1974 back to 2011, but to look at the day of the year that a tornado has occurred and graph it by that. So let's move to the next insight, which is looking at this graph by day of the year. So what I've done here is effectively just dropped each one of those cubes into a bucket representing the day of the year that it took place. So I've got my 42,000 cubes stacked up for a day of the year plot. And you can see there's a very, very clear trend in the data that's easy for me to spot. Tornadoes tend to happen more often in that period of the year. And we can see our April tornado for reference early here. Now, days of the year aren't particularly meaningful to me, but months of the year are. So let me change this to look at the month of the year instead of the day of the year. And I've also now colored it and ordered it by the strength of the tornadoes again. It's interesting to note that the biggest tornado month in those 42,000 records is May, this large peak here. So sometimes it's easier to split these different colors out with their own rows. So I could drop those out, for example, and look at the relative proportion of the different strengths of tornadoes. And you can see that there's a pretty consistent curve around about May time for the most frequent tornadoes to take place. So assuming I found myself in the mid to the mid-eastern portion of the United States, sometimes around May, when should I be most aware that a tornado might take place during the day? So let's look at the hour of the day that tornadoes typically take place. So what I've done here is I've dropped them into 24 buckets corresponding to the hour of the day. And you can see there's a very, very clear peak around about 5 to 6 p.m. in the afternoon. OK. So there's some more insights that I could share in this data, but I think I'll conclude the demo there. What I hope that I've showed you is that you can take a relatively small number of mappings of data in space according to size and color, and you can actually spot patterns that lead to a great deal of insight in that data. And with that, I'll hand back to Curtis, and thank you for your attention. Thank you.
OK, so what's the future of visualization? Well, I think there are about 3 trends that we're paying attention to. First one you just saw here is when we were working on PowerMap, we really focused on not just plotting data on a map, but also to bring in time. So you've seen some of the PowerMap visualizations. You can see things like in Chicago looking at time. Well, that's just the beginning. Temporal analysis and the periodicity in your businesses is a really key thing. And to be able to have tools that everybody can use to do temporal analysis, I think will be very powerful. I think the second trend that's really interesting is what Harry talked earlier about in terms of the invisible intelligent cloud. So if you look at the improvements in efficiency and effectiveness in terms of the accuracy of speech recognition or computer vision in terms of being able to recognize objects, those have improved so much in the past few years. And the reason for that is the combination of 2 technologies, machine learning and deep neural nets. And when you think about that, they're both in a way sort of pattern recognition. And what we do as human beings in terms of visualization that works for us is that we're really great. Nature built us as pattern recognizers. So if you think you can, by using some of this technology to learn from what we're doing and amplify that ability to all this data in a cloud, then I think we maybe have a standing chance to be able to really start to get insight from really large data. And I think the third development is really easy to use, powerful data visualization that will democratize access for domain experts and not just the data scientists to gain insight. So we bring all those three together, I think it bodes really well for the future of visualization and the products that Microsoft's going to be working on. And I want to thank you for this. Thank you very much. I'd like to bring... Thank you, Harry.
Thank you, Curtis. I love data visualization. I hope you enjoy it, and just this kind of smoothness, all those transition effects, and the spatial temporal ways of visualizing things. And you probably already figured out that there was really a real reason why I requested to Brett, I'd like to do this keynote during 5 to 6 p.m. in Chicago. I want to make sure that you guys are safe. So seriously, the opportunity for you, all the IT pros, to think about how to take advantage of data visualization for your daily work, for your organization, is just tremendous. So we look forward to working very closely with you. And for those of you who would like to get in early access to some of our technologies, we are also here to help. So let me move to the second topic, which is a challenging one. And not that the data is not challenging, but this one is, you see a lot of urgency. This year marks 50th anniversary of Moore's Law. What unbelievable law it is. All of us in this room should thank Gordon Moore for what he actually pointed out 50 years ago. We benefited tremendously economically, technologically, emotionally, any way you think about. There is something true called exponential growth after all. And we actually even experiencing it. But likely, every good thing probably has some ending. People have been talking about end of Moore's Law for quite a while. And it's very likely that we will hit the kind of limit of the transistors. How small can we really get? So at Microsoft, we have been thinking about this very tough problem because we need to have this sustained growth of seemingly never-ending processing power. And we know we will need that for our industry, for the experience and the magic we want to create. So is there some good news? So I'm going to share something with you, what we have been doing in Microsoft. And I start with something near term, something very concrete. Then I will also talk to you about something longer term, much more speculative. So near term, we bet on something called programmable hardware. It is something called FPGA, or Field Programmable Gate Arrays. It turns out that you can actually design the hardware, then flash it to FPGAs. Then later on, if you don't like the design, you can change the design, then flash to FPGAs again. Now we're all very comfortable with programmable software, because after all, software is here to be programmed. But the hardware is a completely different beast. Because as you design general purpose CPUs, you actually need to think about all kinds of computations around. So you want to have this very general architecture. That's why you have CPUs. And in our industry, over many years, we also did something called the GPUs. That's actually graphics processing unit. That also was very, very successful for a particular kind of workloads. But even GPUs are tailored for certain workloads, like playing games. Now, of course, there are a lot of study, even moving that to more general. But with FPGAs, we have this unprecedented flexibility to think about the current workloads and the future workloads that we can hardware accelerate. So we started a pilot project about 3 years ago between Microsoft Research and the Bing engineering team. This is actually an article last year, the Wired magazine, talking about what we have done. And we worked with the Bing team and looked at the most interesting workload they had. That's really about the ranking function. As you rank all those web page results, and you have to do a lot of computation there, and we helped the Bing team pilot this program, and we get a factor of 2 acceleration, not to mention about economic gains there. So the pilot is going so well that we actually are going in production. So in a very short period of time, when you Bing something, very likely you will enjoy the benefits that we actually have those FPGAs in our data centers accelerated. So the team actually didn't stop there. Now we actually look at certain workloads in Bing. We thought that we can actually also apply to other workloads. So we have been working with some other teams in the company. Particularly, we actually applied this FPGA to machine learning. So I'd like to roll a video to show you some of the results, how we accelerate the machine learning for image understanding without and with FPGAs. Roll the video, please. So you get this idea there, how fast that we can actually do. So the aspiration we have in Microsoft is that we will build this new fabric of programmable hardware to complement the existing fabric of software, the programmable software. And you can imagine that we will build those hardware to benefit a lot of Microsoft first-party workloads, but we intend to open that up for third parties and our ecosystem as well. So this is really very exciting. So now, the long term, can I get back to the previous slide? The longer term is a lot more speculative, but that's where we're also very, very excited about. And we talked about all those physical limits with the electronics. But that's only part of physics that we have learned. I know, we only probably, most of us stopped there. But there is something called quantum physics. There is some hope to do quantum computing that can overcome, that can sidestep the kind of challenges that we have with electronic computers. We have been very fortunate to have formed a team several years ago in Microsoft with partners like some very famous experimental physicists that we work together, look into some exciting fields in quantum computing. But I'm not going to pretend to be the expert. Instead, I'm going to invite my colleague, Krista Svori, to come up to explain to you some glorious details of quantum computing. Krista.
Thank you, Harry. So I came to Microsoft to see how mathematics and computer science innovation could really reach people in a big way, to really have impact and make a difference in our world. My area of expertise is quantum computing. I really write software for a computer that doesn't yet exist. And why? Because quantum computers will go beyond the most powerful supercomputers. Quantum computing will be as transformational, if not more so, than conventional digital computing over the last 60 years. At Microsoft, we've actually been doing research in quantum computing since the late 90s. In late 2000, Michael Friedman, a Fields medalist, and several of his colleagues at Microsoft showed that computing with a yet-to-be-discovered quasi-particle might actually lead to a paradigm shift for computation. And they called this approach topological quantum computation. Michael Friedman approached one of our senior executives to discuss the company's quantum investment in 2004. And just 2 years later, in 2006, Microsoft's Station Q was founded to serve as a center for the study of topological quantum computation and all of its potential. In 2010, several Station Q researchers actually developed a proposal for how this elusive quasi-particle might be able to actually be seen in the lab. And so one of our research partners, Leo Cohenhoven, took this proposal from Station Q, engineered and built the experiment in his laboratory at the Technical University at Delft, and became the first to detect evidence of the Majorana quasi-particle in April of 2012. This particle had been elusive since it was first thought to exist in the 1930s. And it was shown to be useful for computation by Station Q in the early 2000s. So you may be wondering, what does a quantum computer look like? Well, quantum computers are, of course, still in their early stages. But here's a photo for you. You can see here a photo of our research partner, Charlie Marcus, his lab in Copenhagen, Denmark. On the left is a picture of the lab itself. You can see a large tube, a cylindrical object on the left of that photo. That's a dilution refrigerator. And inside that dilution refrigerator, when you remove the shield, as you can see on the right, sits the quantum chip. And this operates at the coldest place in our universe. Minus 459 degrees Fahrenheit is where this quantum chip operates. And this quantum computer, once scalable and programmable, will be controlled by a massive digital computer running non-trivial software that will allow us to compile and program this very exotic device. Quantum computers will take us far beyond what is possible today by accelerating years of lab work into hours or minutes, and by enabling computations that would take longer than the lifetime of the universe on a supercomputer, and allowing them to actually be computed in days, hours, or even minutes. If we had a small quantum computer today, we already know that it would help us rapidly innovate in a wide variety of fields. Take, for example, health. A quantum computer could help us more quickly identify drugs to synthesize and test before actually doing so in the lab. And it may be able to help us find more efficient ways to produce artificial fertilizer, which in turn could help us alleviate global hunger. In energy, a quantum computer may be able to help us find a room temperature superconductor that could aid in the creation of lossless power grids or maglev trains. In the environment, a quantum computer may actually be able to help us combat global warming by helping us learn how to efficiently extract carbon dioxide from mobile point sources, such as automobiles or airplanes, instead of just at stationary fossil fuel plants as we do today. And I originally joined Microsoft Research 9 years ago to work in machine learning. And now we're actually developing ways to use a quantum computer to improve machine learning techniques, to create better models of users and data, to speed up the learning of these models, and to develop entirely new ways of learning from data and thinking about ambient intelligence. We already know how powerful machine learning can be in the cloud. For example, using Azure ML to understand data, users, customers, and to form better businesses. For those of you wondering just how a quantum computer could actually help your business, imagine the tremendous impact that quantum machine learning in the cloud could have on enterprise services. It could offer better opportunities to learn from and use both internal and customer data, the ability to seek solutions from a quantum computer in the cloud, to ask entirely new questions, questions you would never be able to even ask a conventional digital computer. Think of the benefits that could have for productivity, efficiency, and communication. My team and I are inspired by the promise and potential of this new model of computation, a technology that will literally take us quantum leaps beyond what we can imagine today. Thank you very much. Thanks, Harry. Thank you.
Thank you. I hope you are as excited about the future of quantum computing as much as I do. But you have to wait a few more years to get your hands on the quantum computers with enough number of qubits that actually are stable and can perform some difficult tasks. This investment in quantum computing really educated me that only through this kind of long-term investment can we actually learn, is this actually a 50 years investment, or is this actually more like a 15 years investment? I feel like we are not that far from seeing real quantum computers. It's pretty exciting. The third and the last problem I want to talk to you today is about the intelligence. It's about the limit of mankind. It's about what we should do with that much computing power. This past year, I would say the hottest buzzword has been artificial intelligence. It's not only nerdy people like us talking about. It's everyone's talking about. Those business people and even Hollywood people. They even make movies. So if you think about that, you say, some people really worry about, is artificial intelligence getting to a point that there exists super intelligence that will overpower human intelligence? Some people do have some extreme views. As someone close to the science and also as a practitioner, I see more like a continuum. I see AI more like a continuum about complementing human capabilities and helping us to get more out of the computing around us. So today, with limited time, I'm going to drill down to one area of artificial intelligence called computer vision. It's an area that I have studied for 25 years, and I want to take you through some very interesting journey and also milestones recently. Talking about a long journey, in the early 60s, Professor Marvin Minsky at MIT proposed that as part of AI study, we should just hook up the computer with the camera, then see what the computer can tell us. And I remember when I went to Carnegie Mellon to study for my PhD, I told my advisor that I'd like to study computer vision, and he asked me why. I said I read somewhere that more than 90% of the information that the humans receive actually is through the visual system. So that's why I would like to study computer vision. But it has been a long journey, and it's taken generations of great researchers to get to where we are today. But today we see very, very exciting results I want to present to you. Last summer, we actually showed the first time that we built a system that can actually recognize dog breeds, different kind of dogs. We actually built a sophisticated distributed system doing deep learning. And we were able to build a very efficient system that was actually 30 times more efficient compared with the state of art at that time. Then you might ask me, why does this have anything to do with me? So now you can recognize dogs, so big deal. Well, not so fast. Let me show you our continuous progress here. Only several months later, we were able to build the system, again, using very deep neural nets. For the first time ever, we were able to show that computers can really outperform human beings in recognize thousands of object categories. You may think that we humans are very capable, but it turns out that the error rate for human recognition, when you push that to thousands of categories, even after a certain amount of training, is actually going to be around 5% of the error. So we were able to really beat the human performance for the first time being. So then we thought about, what are we going to do with that? So the right idea we came up with is actually democratize this whole field of machine learning, computer vision, by sharing the kind of APIs, the tools we have with our developers and with our partners. So last week at the Build, I announced this set of REST APIs we call the Project Oxford, that anyone can just call cross-platform because it's really REST APIs, and build your own apps so that you can add intelligence and smarts to your data, to your app. And a couple of our devs in Microsoft spend less than a day to just put up a website just to show off the capability there. Oh boy, it went viral. So the site is called how-old.net. It's unbelievable. In case you haven't tried it, you better give it a try and see how old you are. And share with your friends. Last time I checked, that website has been shared on Facebook for more than 1.3 million times, only in a few days. So that sounds exciting, but we continue to work on, and with some very, very interesting computer vision results. I'm going to show you some latest results. In fact, we got this result only last few weeks. That is really object recognition and the video segmentation down to pixel level accuracy. Can we roll the video, please? I hope you have seen I'm very, very proud of the results, and I have been working this field for long enough to really appreciate how hard it can be. I will tell you honestly, even a few years ago, no one would have imagined that we can get to this level of accuracy. We can do object recognition and the video segmentation down to pixel level, and that accurately. And keep in mind, it's all done automatically, with deep neural nets that we trained. And you look at that, you will see the complexity there. You will see the pictures in the indoor versus outdoor. You will see big objects versus small objects. And it's different kind of lighting conditions. So this is really going to have a lot of interesting applications for us. And I show you some very quick examples where you can apply computer vision technologies, whether it's in healthcare, and you can certainly identify counterfeit drugs, and you can look at patients' expressions, understand whether they actually need help. And you can also apply this kind of technology to different kind of industry segments. Think about all those robots on assembly lines. Most of them don't have visual capabilities. They might be accurate, they might be efficient, but they are not really intelligent without this kind of visual capability. And we can add this capability there. And you don't have to go to assembly lines to enjoy this kind of benefits brought to you by computer vision. for your daily life, if you care about what you eat, more and more people are very calorie conscious, I'm afraid. Take a picture and you can build an app, depending on the kind of data you can have, you can identify how many calories you have for the lunch you had. So I'd like to come back to the slide I started earlier. That's really the slide of the 3 ambitions Satya put together. You have seen only a small subset of the work that we have been doing in Microsoft Research. In the future, you can expect us to do a lot more work in machine learning, augmented reality, artificial intelligence, to help create more personal computing. You can expect to see a new set of tools and visualizations and experiences, including data visualization, new user interface, ambient intelligence, as we reinvent productivity for personal and business use. You can expect more disruptive technologies coming out of Microsoft as we build the most intelligent cloud, most trusted cloud, as we come up with these new architectures, together with the right economic models, with the right hardware and the software, and most importantly, with the collective intelligence that will power a lot of applications you need to build. I come back to this quote by Arthur C. Clarke, but I actually would like to build on top of that. I would say any sufficiently advanced technology is invisible. So advanced, it disappears. As computing moves to the cloud, it disappears, yet it becomes more powerful. As machine learning works at its best, you wouldn't even notice it. Yet, the results, as I've shown to you, are incredible. As the user experience is integrated with the surrounding environment, wherever we go to, we don't see the computers, yet we can interact with the computers using gesture, voice, facial expression, gaze. It just disappears. In my view, an invisible revolution is coming, that we are at this stage by applying the right technologies to have the right product forms with interesting business models. We will create magic together. And the magic like breaking down language barriers, like we recently have done with the Skype team to create the Skype translator. Roll the video, please. Thank you very much.
Hi, can you guess where I live?
¿Te encuentras en América del Norte?
Yes. Do you live in Central Mexico?
Sí. ¿Te encuentras en Estados Unidos de América?
Yes. Do you live in a capital city?
Sí. ¿Estás cerca de Seattle?
You're very close to Seattle. Are you in Mexico City?
Sí. ¿Estás en Tacoma?
Yes. Very good guess.
Gracias.
Thank you.
Do you like living in Mexico City?
¿Te gusta vivir en la Ciudad de México?
Aquí está muy lindo.
Here is very nice.
What do you do for fun?
¿Qué haces para divertirte?
Voy a las playas de México.
I'm going to the beaches of Mexico.
I like to swim.
Me gusta nadar.
A mí también.
Me too.
Where in the world do you wish to travel?
¿A dónde en el mundo te gustaría viajar?
A Rusia.
To Russia.
¿Y tú?
And you?
Everywhere.
Sería increíble algún día verte en México.
It would be amazing to see you someday in Mexico.
I would really like to visit you sometime.
Me gustaría mucho visitarte algún día.
A mí también.
Me too.